Welcome. This is the 7th video in the series on Principles of Radiographic Exposure 1. In the last video, we learned secondary factors and how they affect the image process. In this video, we will expand on the lesson from video 3 of this series, where we had an introduction to technique. We will discuss what technique is and how the parameters can be utilized to produce a radiographic image. We will also talk about quantum mottle and exposure indicators. There are two parameters that the radiographer can change that affect the amount and the energy level of the X-rays produced during exposure. They are the kVp and the mass. The kVp and mass that is set or utilized during the exposure is known as the technique that is used. The kVp is the kilovolts peak, and the mass is the milliamperage seconds. The kVp controls the quality and the quantity of the beam. So the quality is the energy or the penetration of the beam, or other terms that could be used for the quality of the beam. And the quantity can also be the amount of X-rays. It can also be called the intensity of the beam, the quantity. So the quantity is how much, okay, and the quantity is the energy that's contained in the beam, or how, you could say how strong the beam is, okay? The quantity, the quality of something, right? And the mass only controls the quantity, so the mass only controls the amount of X-rays, where the kVp controls the quality and the quantity. So that's important to keep in mind. First, we'll talk about kVp. The kVp set will be the highest energy the beam will contain. The energy of the beam is also known as the quality of the beam. As we talked about, the higher the quality of the beam, the more penetrating the beam is. So the quality and the penetration of the beam are directly related. The higher one is, the higher the penetration is too. The percentage of X-rays that penetrate through the patient is a direct function of the average energy of the beam. The average energy is increased with an increase in the kVp. And we can see here, this is the diagram. This is the graph of a change in kVp. So with a change in kVp, the energy goes up, and it will only go up to that peak. So the kVp that's set here is 82. So the highest that energy that can possibly be contained in this beam is 82. Okay, keVs. All right, and in this one it's 72. We can also see if we took the value and how much of each one of these there is, okay, each one of these quantities all the way through each one of these graphs, the average energy of the one that's set higher, that's set to 82, is going to be higher. So the average energy is increased with the increase in kVp as well, okay? And the average energy of the beam is what we need, okay? Or is what we're interested in for the penetration during imaging, okay? So there's another way to increase the average energy of the X-ray beam as well, and that is filtration. If we increase the filtration, we'll increase the average energy of the beam, as we talked about in the last video, okay? This, of course, won't change the peak set. The only way to change the highest energy that's set, or the peak that's set, is by changing the kVp either up or down, of course. So let's look at this here. We have the primary beam that's produced, okay, and then we have the remnant beam. And in order to form an image, we want a certain number of absorption events to occur, and we want a certain number of transmission events to occur. We don't want necessarily any scatter events to occur. That's only going to cause fog and cause more grayness on the film, but we can't prevent that. Okay, we can't prevent the scatter events to any degree. We can change how many occur based on the kVp we set, which we'll talk about a little later again, all right? But the higher the kVp set, the more penetrating the beam will be. Okay, so this means that the more transmission events will occur. All right. However, the beam is not homogenic. So if we set the KVP at a certain level, all the energy is not going to be set at that level. And we saw that in the graph before. It was a curve. Okay. The beam is radiogenic, or it's polyenergetic. Might be a term that the textbook uses as well. It has energies from the highest point set to just above zero. Okay, so it has energies from the KVP set all the way down to just above zero. This is actually a good thing, because if it was only one energy, the image would have little to no contrast. If the beam was only one energy, it would either penetrate the part as a transmission event and make a blackness on the film, or it would get absorbed and it would never make it to the film and it would show up as white. So the film would either be very, very white, the final image would be very, very white, or it would be very, very black if it was only heterogenic. Okay, so the thing to remember about the X-ray beam is that it has many different energies. Okay, and this is beneficial for us that it behaves this way, because we're going to have a certain amount of absorption events with the lower energies. We're going to have a certain amount of transmission events, and our job or our goal in setting the KVP is to set it at a level that there's enough transmission events that it creates an image, and there's also enough absorption events that we have contrast within the image. There's always going to be scatter events, and we can change that depending on the KVP that's set, and we'll talk about that a little later. We'll actually go ahead and we'll talk about that right here. From the previous lesson, which I believe was video 5 on interactions with matter, we learned that the probability of Compton interactions is 1 over E. So 1 over the energy level of the X-ray. Also, the photoelectric effect probability is 1 over E to the 3. And it is also affected by the atomic number, which is the Z number to the third. We can't control the Z number, which is the anatomy being X-rayed. We can't control what the Z number of that is, but we can control the energy levels that we set. Compton is a scattering event, and it causes fog, which we don't desire fog. It only creates a grayness on the film that is non-diagnostic. And we can see that with the higher KVP set, the less likely a Compton event will occur, right? Because the larger this number gets, the smaller the number will be. But the far less likely a photoelectric event will occur, because this is to the third. So this is going to drop off much, much quicker. And we can see that represented here with this graph, where Compton's represented in the purple. So it's 1 over E. And then the photoelectric effect is represented in the blue. So as the energy level gets higher, Compton occurs at a far greater amount compared to the photoelectric effect. It's occurring at a less amount, but it's greater compared to the photoelectric effect. And we want the photoelectric effect to occur because that's the absorption event. We want absorption of the beam and transmission of the beam to create that contrast where the anatomy is well represented. Okay, we need a certain amount of transmission and absorption events to create the brightness that's ideal for diagnosis. Okay, and also for Compton, also for contrast. KVP and patient dose. The higher the KVP, the lower the patient dose, as more of the X-rays will be transmitted through the body and won't interact with the body at all, because it will have the penetration just to go right through the tissue. The lower the KVP, the higher the patient dose, as more of the X-rays will be absorbed through the body. And we can see here, this is just a quick little thing. So of the X-rays coming in, these 4 waves here represent all the X-rays coming in, let's say, and it's hitting the same tissue. Okay, so the one on the right is going to be a higher KVP as more of the X-rays are being transmitted through. Okay, so only one of these 4 right, in this representation, is being absorbed by the patient. So the patient's only getting that dose of that one. And in this one with the lower kVp, they're getting 2. Okay, so they would be getting twice the dose because they're absorbing 2 of the X-rays waves here. Okay, so this is why we need to balance the kVp out. Okay, with what is desired for the image and patient dose. Let's go ahead and talk about the 15% rule. So as mentioned before, the kVp changes the quality and the quantity of the beam. And this is summed up in the 15% rule. So how it changes the quality of the beam is pretty obvious. We saw that in the graph earlier, right? The quality is going to go up. It's going to shift to the right. There's going to be a higher percentage of more energetic rays, and the peak is going to be higher, okay, as we increase. But it also increases the amount of them. The 15% rule says the increase of 15% in the kVp will double the quantity, which is the amount of the beam, and a decrease in 15% of the kVp will reduce it in half, of course. In order to adjust the quantity of the beam, the mass should be adjusted to half when kVp is raised by 50% and doubled when kVp is lowered by 15% in order to maintain the same quantity of the beam. Lowering and raising the kVp by 15% can be too great to maintain relative contrast. Therefore, in practice, changing the contrast by 5% may be beneficial to understand. So we're going to change the contrast. I hope that's clear. We have the potential of changing the contrast of the image by changing the kVp because there's going to be more of that transmission absorption or less occurring, okay, as we change the kVp. So changing the kVp by 15% is what this is saying, might be too great of a change. Okay, so a 5% change may be beneficial. An increase in 5% of kVp requires a 30% decrease in the mass, and a 5% decrease in kVp requires a 30% increase in the mass, okay, to maintain the IR exposure, if our goal is to maintain the IR exposure here. Okay, so an increase of 5% is 30%, 15% is doubling, okay, or halving. So with that, we're going to go ahead and we have a few questions on the 15% rule, just a few mathematical questions. I encourage you to pause the video here, go ahead, solve these 3 questions. The answer will be at the end of the video. So this is something I did based on the 15% rule. So I graphed the 1-to-1 of mass to the original kVp, and then I used the 15% rule and I increased the mass by double each time. So at 15% it's double, at another 15% it's double, and I used this, and now we got I made a trend line and an equation, and we can extrapolate some things from that to see the 30% rule and see how that works. So originally, if we have 80 kVp and we have 20 mass, and we increase by 15% the kVp, what should the new kVp be? Okay. With this, it says that we're going to decrease the mass by half. The new kVp will be 92. Hopefully you thought about that. The new mass is going to be 10, and that's just using this equation. Okay. In theory, it should be 10. Using this graph that I created, it's 10.11 because there's always going to be some amount of error. So now if we make this 85%, we're reducing by 15%. The new kVp is going to be 68, right? And the new mass Well, I'm trying to hide it, I guess, but you already saw it, okay? So now we're going to go ahead and we're going to increase by 5%, okay? In theory, it should be a decrease of 30%, right? And that decrease in 30% is going to be the 15.38. Okay, and we'll do the same thing where we decrease the kVp by 5%. So we go from 80 to 76, which is a very doable amount in practice. That's about what you would lower it if you're lowering the kVp typically. Okay, I'm going really fast here. So, and we can come up with any kind of thing. Okay, the theory doesn't have anything for lowering it 10%, but 80 to 72 is very doable, and we would want to go to 30. Okay, you're not going to remember these necessarily, but it's just a way to see that using that relationship, how things, how even when you do things in a different way than just straight that relationship, how this comes out. So this is a very useful graph I made just to kind of prove the 30% thing too. Now if we reduce it by twice 15%, what I just did, I increased it before, but we're going to have to half it and then half it again. So the original was 20, so we're going to half it to 10, then we're going to half it, and it should be 5, right? But it's coming out 3.7, okay, because math equations aren't always going to work exactly, okay? And we can put in any values in here, okay? And we can see if we go from 75 to 63, we decrease 15%. We're going to have to double the mass, okay? If we increase the kVp by 5%, we're going to go by 30% down, okay? In theory, it should be this. Using this graph that I created based on this rule, it comes out at 15.5, okay, which is very close. And you can see we can do any kind of, I could put any kind of numbers in here and it comes out, okay? So 6.4 to 5, that's the next step, which when we, in radiographic physics, we'll talk about the generators, and you can learn why there's different steps of mass if you pay attention on the console. When you're setting a fixed technique, why there's different sets of mass that are available, and it will be discussed in physics. But 6.4 to 5 is the next step, okay? So it's very convenient, let's say, that the equipment is designed in such a way that a minimum increase in kVp that might be done, okay, from 85 to 90 on an exposure is also allows the same necessary change in mass from the 6.4 to what should be 5, okay, and with this it comes out to 5.97 with the graphing data, that it allows that, okay. Most systems are going to go 6.4, and the next step that is available is 5, okay. And if I work through some more of these right here, it does work out very close to where the available steps of the mass are is what this comes out to, the next available step, okay, quite often. So this is just an interesting tool I came up with, and we could see how that changed, how things changed as we put in different data there. We'll continue our lesson on kVp. If tissues are not penetrated, they will appear homogeneously white on the image. If they are penetrated too much, they will appear black. So the most important function of kVp is to provide partial penetration through all the tissues that are recorded at the proper level. All tissues will be represented, okay? So our job is to set a kVp where this occurs. The kVp will affect the contrast of the image, okay? Typically, the desired contrast of a radiographic image is set by the radiologist and by convention. Therefore, KVP is usually set for a given exposure, and the mass is adjusted to achieve the desired exposure to the IR. With that, this is a note on digital here, is contrast is adjusted by the imaging software and by the image processing. If you would like to know more about how this is achieved, the topics are explored in the playlist of Principles of Radiographic Exposure 2. Okay, but the KVP can change the contrast, because if we have it set too high, there will be pure penetration and it will be too black. Okay, the final image may come out too black. The imaging software is gonna adjust it. Okay, but a certain point that breaks down. All right, so we need to have a proper KVP set. All right, so let's go ahead and let's look at some actual images of different KVPs that are set. So we can see the number that's set here. So this is 58 kVp, and this is of the distal upper leg. Okay, and we go through the different settings. Okay, and with this, the mass is staying the same, only the kVp is changing. So at a certain point here in these lower ones, perhaps the penetration, especially with this 58 here, right? We can't see very much in the patella area or up in here, okay? And with the 80, which would be kind of more of a typical setting, we can see some details through here. There is some the proper level of contrast, I'll say, to it, all right? Where as we increase, now we're losing some of this detail here, okay? It's penetrating. There's too much transmission occurring in these parts. Okay, and then here it's either much more where it's just white. We kind of lose some of this detail in here that we had on these lower KVPs, and this is penetrated far too much now. So there's way too much transmission going on in here as the KVP rises. Okay, so this is an example of how the KVP can change the look of the image, even with the imaging software. Okay. We'll move on and we'll use the 15% rule now. So we have the same KVPs that were set on the last one, okay? But we're changing the mass as the KVP is increasing 15%. Each one of these is a 15% increase, okay, in the KVP. So we go from 16, we are increasing the KVP by 15%, and we're halving the mass, okay? This is 80 at 4, this is 92 at 2, and this is 105 at 1. So you can go ahead and look at these images and you can decide what's happening here. So there's many different factors at play, of course, when we're taking an image, and we need to take all those into consideration. All right, the patient dose, the look of the image, okay, and all these things. But I'll point out though that you can really see here that things, I would say, are much more either white, okay, they're either not penetrated, or they're black, I'll say, okay, where here we have some more contrast in this area, okay. The total brightness, I would say, of the images which would be the total IR exposure, are about the same in all these images, I will say. It just depends on the anatomy, okay, that's being visualized, right? So so this is an example of the 15% rule at work. We'll go ahead with that, and we'll move on to mass. The mass of the X-ray exposure is only changes the quantity. A change in the mass will affect the number of X-rays the same amount as the change in the mass. So if we increase the mass by 30%, it's going to change the amount or the quantity of the X-rays produced by 30%. Where with KVP, we increased by 15% and we actually doubled the quantity. So a mass is a much more direct relationship with the quantity. So if the mass is doubled, the number of X-rays produced is doubled, and we can see that right here. This only says MA, but if we double the MA, we're also doubling the mass, okay? So it doesn't change the quality of the beam, okay? So the average energy of both of these will be the same. The peak energy will be the same, that's the quality of the beam, but the amount will double. So at every point there'll be twice as many. At each energy level there's going to be twice as many because we went from 200 to 400. We doubled the mass. So a change in mass can be accomplished by changing the MA or the time, which is the seconds, which is the S of the exposure. MA is a combination, or mass is a combination of the MA and time, and is summed up in the equation mass equals the MA that's set times the time. Therefore, doubling the time will double the mass, and doubling the MA, as we saw on the last graph, will also double the mass. All right, so the number of X-rays that reach the IR is directly related to the mass. Since the mass is a combination of the MA and time, it doesn't matter as far as the intensity to the IR is concerned which combination of MA and time is utilized in order to achieve the quantity of X-rays in the primary into the remnant beam. So it doesn't matter what combination of MA and time you use, as long as the mass is the same, it's gonna have the same amount, it's gonna have the same quantity of X-rays in the primary beam into the remnant beam, which is gonna get to the IR. So as far as the IR is concerned, which is the signal for the image, it doesn't matter what combination of the MA and time you use. Therefore, an exposure where the time is halved but the MA is doubled is effectively the same as the original, as the exposure, okay, where the time started out as it and the mass was half, or the MA was half. And this is an example of that right here. So we have 200 MA set, and it's at 0.08 seconds, which is also, you could say, 80 milliseconds. Okay. You can change this to 400, so you doubled the mass here, or you double the MA here. Keep saying mass. You double the MA here, and you have the time. Okay, and both of these are exactly equal. They're both 16 mass. Okay, so you can take the time, you can multiply these two out, and you can see that's true. All right. Also, if you have 500 MA at 0.02 seconds and 120 MA times 0.08 seconds, it's going to be 10 mass. They're both going to be equal. So what happened here is you halved this once, you got the 250, you halved it again. So you divided this by 4 essentially to get to 125, and then you multiplied the time by 4. So the time is 4 times longer. How long the exposure is going to go on for? It's 4 times longer. And the MA that was set is a fourth of what it was. But the resulting mass and consequently the exposure to the IR is going to be the same. It's going to be 10 mass that is produced in the primary beam. Okay. So I hope that's clear. So as I mentioned before with the, I believe it was the 20 milliseconds or 80 milliseconds, okay, it's easier to say 80 milliseconds than it is for us to say 0.08 seconds, okay? They're both the same thing. So we have a possible issue that can occur when we're trying to figure out what the effective mass is actually going to be. because it may be presented in milliamperage and milliseconds. Okay, and we don't need the total to be milliamperage milliseconds. We need it to be milliamperage seconds. So this is just something to watch out for with a question that might be presented to you. Time, when it's displayed on a console, when the technologist speaks of it, as we said, is usually expressed in milliseconds. This is done for ease of understanding. It is easier to say 20 milliseconds, that is 0.02 seconds, or 2/100ths of a second, okay? It's easier to say 20 milliseconds, would typically be how we say it. We could say 2/100ths of a second also, which this 20 is effectively 21 thousandths of a second, okay? This right here. This can create a problem when we discuss mass, because we express amperage as milli typically in the way that we're using it as well. So we're expressing two things in milli. So this can create a problem when we're doing a question. So make sure when calculating or thinking about mass, you keep your units correct and you end with milli. So we have 200 MA at 20 milliseconds. This doesn't equal 20 MA times 20 milliseconds, okay? Which that would be 4,000 mass, okay? This should equal 4 mass, all right? So doing it this way, so just taking the numbers at their value isn't gonna work out to a correct answer, okay? So there's two ways to perform this. One is to keep the forms a milli and then to convert, which may be slightly more confusing, and then we'll talk about the other way. Whichever way you decide, or maybe there's another way of thinking about this, as long as you have it straight in your head, you need to make sure that you're aware of this milli. Okay, so this is a unit issue because we want to end in milliamperage seconds. We don't want to end in milli amperage seconds, and we'll see how this goes right here. So this question right here is effectively actually saying 200 amps times 10 to the negative 3, which is the milli, okay, suffix or prefix, okay, times 20 seconds times 10 to the negative 3, because milli is 10 to the negative 3, okay. So if you multiply this out, you're getting 4,000, okay, which that part is correct, but you're getting times 10 to the negative 6 seconds, okay. So this is actually micro, so you're getting 4,000, I guess it would be microamp seconds. Microamp seconds is what this is equal to right here, not milliamp seconds, okay. We need to get to milli. We need to get 10 to the negative 3, not 10 to the negative 6 for the final answer. Okay, so that's where the problem's coming in. So the one way we can do it is we can divide, okay, the answer by 10 to the 3, okay, this part. We can also multiply it by 10 to the 3. When we divide and we multiply the same number by a number by the same number here, we're effectively just multiplying by 1. Okay, you can multiply anything by 1 as much as you want in mathematics, because it's gonna be itself. We're just converting the units is what we're doing. So we're converting from milli or micro to milli here, okay? So this 10 to the 3 times 10 to the negative 6, if we remember from the math lesson early on in this series, it will go to 10 to the negative 3. These two just add together, essentially, when the base is the same, okay? And this is the same as moving the decimal point over 3, okay? Or dividing by 1,000 is what this represents right here. So we're dividing by 1,000, so it comes out to 4 amperage, and then this will be to the negative 3, okay? And that 10 times 10 to the negative 3 is what we want. This is milliseconds. So now we can, instead of writing it this way, we can write milliseconds, and then we can write it in the form that we know as 4 milliseconds. This is just something to be aware of. Another way to do it is to convert the seconds to milliseconds it should probably be milliseconds to seconds, and then multiply. So we just convert this 20 milliseconds to seconds, okay? And then we just multiply it out straight like this, okay? Because we're already in seconds here, so, and we're already in milliamps, okay? And so the other thing to also watch out for is it may give it to, a question may give you amps, okay? It may give you amps, so also look out for that. So just watch your units, and these are two different ways to go about getting the correct answer. If the seconds is in the hundreds, so it's 0.x, okay, then it's 100 milliseconds. If it's in the tens, like this spot right here, it's the tens milliseconds. So this is 20 milliseconds because it's in this spot right there, 0.0x, okay. And if it's in the ones like this, where it's 0.00x, okay, then it's individual milliseconds. Uh, so if this said, instead of 20, if it said 2 milliseconds, we would have to write 0.002, okay, and then multiply it out, and that would be effectively 0.4 mass, which isn't something that would necessarily be used in practice necessarily. I guess it could be on a small child or something, um, but this is the way you would convert the presentation of milliseconds to a decimal point, okay? You're effectively just dividing by 1,000, okay, is what you're doing to get from this to this, okay? So let's move on from that, and with that, we will have a couple of just quick questions, and I encourage you to pause the video again, write them down with the KVP 15% rule questions as earlier, and go ahead, we'll have the answers at the end. We'll continue talking about mass. Mass is often the preferred choice, as we talked about, to change the exposure characteristics during radiographic imaging production. What makes mass the appealing choice is because mass only affects the quantity of the X-rays that are being produced during the exposure. The KVP will change the quantity, the penetrating characteristics of the X-ray beam, and it could possibly change the subject contrast. A repeat for technique, the mass should be changed by at least a factor of 2. If we need to repeat the study, if we feel like we need to repeat the study because the technique isn't good, either we didn't use enough or we used too much, we need to change it by at least a factor of 2, either decrease by 2 or double by 2. Okay, we usually won't repeat for an overexposure. Okay, and we'll talk about that a little later too. Let's look at some images with the mass changing. Okay, so we can see the different techniques here. We have, this is 80 at 4, all right, and then we double the mass here, and we double the mass again, all right, and here we half the mass, the 80 at 2, and we're halving it at 80 at 1. So depending on what is desired, okay, depends on what is an acceptable image, okay. I would say clearly, once we get to this point, there's the quantity of the x-rays that we are producing is so great for this tissue that with the penetration, so much is reaching the IR that it's representing all this area as black, okay? And we can't see any details in here, all right, because it's just blackening it all out, and it's even working to the thicker part of the leg up here, right? But as we go down, we can really see the skin well represented, okay? And this is only changing the quantity, okay? There's the penetration of the beam is staying the same through here, okay? It's just because there's more x-rays reaching the IR because we're producing more as we're changing the mass, that it's representing it more and more dark on the final image, okay? So here at 1, we can really see the skin tissue in here, right? But there's not so many rays that are that are making it that are penetrating this area. Okay, the quantity of the rays that are penetrating this area here is lessened, right? So we're losing possibly some detail, especially in here, right? Where when we get to here, we can really see these muscles right here, well represented, okay? And when we get to here, it's too much, okay? And each time we're doubling the mass. So this is how mass will affect the final image, a representation of it here. Let's talk about motion on the image. So the motion is a huge killer for any image when you're taking an image, a picture on your own, right? And if there's any kind of motion involved in it, it will be blurry, it'll be unclear. It's hard to see details in it, right? The same with radiology. So patient motion during image capture is detrimental to the quality of the image in radiology or in normal photography. When a patient is uncooperative, doesn't hold still, and does not hold the breath during the exposure, motion can occur, okay? We have them hold their breath so they're not moving the diaphragm, so things are stagnant, right? Okay? Um, that's why we ask patients to hold their breath, right? But if they're not doing that, okay, it's more likely or even maybe even probable that motion's going to occur. Okay, there's ways to minimize that. The best way is to communicate with the patient about the exam as a whole and step-by-step instructions through the exam. Okay, if we can let the patient know what we're going to do, what's to be expected, it can calm them down, and it can also make them more cooperative during the exam. So communication is best. Sometimes communication isn't enough. Okay. In addition to the communication, motion artifacting on images can be reduced or all out eliminated by the radiographer. We can do this by decreasing the exposure time to a minimum amount. Short exposure times effectively freeze the motion and can capture the close to instantaneous point of the image. In photography, we can call this shutter speed, okay? How quickly it opens the aperture, okay? And it can effectively freeze that one point in time, okay? So this was taken with the person swinging and hitting the ball here, right? But we can see the bat perfectly, okay, because of the shutter speed, because of the time the image was captured in, okay? This ball is maybe slightly blurry or clear, but also physics, when you hit the ball, it deforms. So there might be a deforming effect going on here where the ball is actually clear, but it's actually being deformed at this instant, okay? But beyond that, the shorter the exposure times are advantageous in instances where motion cannot be controlled, as in the beating of the heart, okay? In a chest radiograph or peristaltic motion of the abdomen. Okay, so shorter times are advantageous for not only motions that the patient's in control of, let's say, but also motions that they are out of control of. To accomplish this, a fixed technique can be set and the time can be reduced. In order to reduce the time and maintain the desired mass, the mass will need to be increased, right? So if we want to make the shortest time, we need to increase the MA, probably the highest that is allowable by the equipment, right? An example here is 200 MA at a half a second, okay, or 500 milliseconds, all right, will equal 100 mass, okay? Or we can use 1,000 MA, so we went up 5 times on the MA, and with that we can go down 5 times on this on the time, okay? So we can reduce the exposure time by 5, all right? And we got 100 MA. If we're only using 10, instead of using 100 milliseconds, we can use 10 milliseconds, okay? And I believe that we blink in 25 milliseconds. So this is incredibly quick. So a skilled radiographer all right? We can capture the image at an instant, okay? So quick um, by using these, I'll call them techniques, by using these techniques, okay, on the console when we're setting, okay, the what the exposure is going to be. If we're using the AEC, the automatic exposure control, the MA station can be raised, and this will reduce the time that it is exposing, okay, because the AEC is the one really controlling the exposure at that point, right? It's going to shut it off when it decides it's exposed enough. So we want to raise the MA station, and the time will be reduced to maintain the mass. Okay, the goal is time reduction. For more extreme needs for time reduction, the KVP can also be increased. So we can increase the KVP by 5% or maybe even 15%. Okay, we keep the MA high, whether we're doing a fixed technique or we're using the AEC. Okay, we keep the MA high. This will allow the time to be reduced. Okay, if we're using the fixed technique, we can reduce the time manually, or it will adjust itself, or the AEC will be able to expose for a shorter amount of time. Okay, and we can get that exposure even quicker if we increase the KVP. In extreme cases, okay, we can bump the KVP up. So quantum mottle. Quantum mottle is an insufficient amount of X-rays reaching the IR. It appears as a blotchy or grainy appearance of the image, and this is what it looks like here. Okay, so is this graininess really in this image is what we're looking at here, and that's quantum mottle. So the solution to reduce quantum mottle on the radiograph is to increase the amount of quanta that reaches the IR. Okay, and the amount of quanta is the amount of X-rays. That's the quanta that we're dealing with here. This is done by increasing the technique. Usually we increase the mass. To achieve the dose level of patients as low as reasonably achievable, there may be a degree of graininess on all radiographs. Okay, that's perfectly acceptable. All right. However, too much graininess, extreme graininess, all right, will make the image difficult or impossible to read, okay, and diagnose. Therefore, a trade-off between the image quality and the patient exposure must be reached by the radiographer, okay? So quantum mottle should kind of always be present, okay, because if it's never present, we're just using so much technique, we're really overexposing the patient at that point, okay? But we also need it to be low enough, okay, that the image is of high enough quality that it can be read and diagnosed, okay? Technique and distance, we'll talk about technique and distance real quick. If the distance is doubled, the mass will need to be quadrupled, okay? And this is because, and this can be summed up in the direct square law or the exposure maintenance formula, okay? So this was talked about in video 3 of this series, technique intro, emission spectrum, and beam propagation. But the equation for the distance is the inverse of the square of the distance, okay? So if we go from a distance of 2 to a distance of 4, so we've doubled the distance, now we have a 1/16 of the exposure to the film compared to a 1/4 of the exposure to the film, okay? It doesn't matter what a 1/4 or a 1/16 is, it's unitless as far as we're concerned, right? So, but the point is that when we double this distance here, we have a 1/4, okay? This is a 1/4 as much reaching the film as originally. So in order to maintain the direct square law, or the exposure maintenance formula is utilized. And this is summed up right here. So we have the original mass divided by the new mass equals the distance squared. Okay, the original distance squared. This is a 1 here, this is a 2, so these need to line up properly, right? When we're setting this up, times the or divided by the new distance, we can say, or distance, or the distance to. It doesn't matter. However we label them, as long as we're consistent with the labeling, okay, squared. So if we go from 44 to 72 inches, let's just say, as an example, a real life example here, because these are the distances we would use. Okay, so we'll just label the distance 1 as 44. We'll label the distance 2 as 72. Okay, and we'll label the mass 1, okay, of 10 MA. So what mass do we need to use? Okay, is what we're asking here. What mass do we need to use if we go to 72 inches from 44 inches and 10 mass was acceptable, an acceptable exposure, okay? So we set up the equation here as we talked about, okay, 44, 72, and we put the 10 here. Now we just cross multiply this out, okay? The 10 goes with the 72 squared. The 44 squared goes with the unknown new mass. And then we just divide by 44 squared here, okay? And we get this, and that's going to equal what the new mass is. We just can do this out just like it is. We get 26.8 mass. So we went from 44 to here to 72, which is less than double the distance, right? And we've gone up 2.6 times, 2.7 times from 10 to about 27, right? If we went from 40 to 72, it would be 32.4 mass. So we'd go up, 3 times for not even doubling the distance. More than 3 times the mass is what we need, okay? So this is the exposure maintenance formula. As the distance is changed and the intensity of the primary being directed to the patient will change by the inverse square of the distance. As we talked about before, distance will have no effect on the quality of the X-ray beam. Okay, distance will have no effect on the quality of the X-ray beam. This is controlled by the KVP. It can also be controlled by the filtration. However, KVP has an influence on the quantity of the beam, which we talked about in the 15% rule. This must be taken into account. If distance is doubled, KVP can be raised by 15%, right? Plus another 15%, right? Because we need to go up 4 times. Or it can also be done by a combination of 15% rule and doubling the mass. So we can double the KVP, or we can not double we can raise the KVP by 15%, and we can double the mass, and that will be the same as effectively the exposure to the IR, raising it by 4 times. Okay, so examples of the double 15% rule is we start at 60, we multiply by 15%, we multiply by 15%. Now we've doubled it twice, which is quadrupling. Okay, and we've gone to 79 kVp. We've quadrupled the quantity of the beam, okay? Of course, we've changed the quality of the beam, how much penetration is going to occur too, okay? But we're not taking that into effect right now. Here's some more examples. So if we're at 70 and we do this double kVp thing, we go to 92. If we're at 80, we go to 106. If we're at 90, we go to 119. Obviously, this is very limiting, right? So that's where the combination of maybe the 15% rule and the doubling of the mass, okay, comes in. And this is another reason why, right here, this is another reason why the mass is the preferred choice for the exposure adjustment, okay? Because if we're changing the distance, all right, it could be extreme, okay, and we run out of really what our equipment's capable of here, okay, to go from 80 to 106 kVp, all right. So this is why mass is typically the preferred choice. Let's go ahead and let's start putting some things together. The kVp that is set at the console by the radiographer during image production will be the penetration of the beam. A sufficient kVp is necessary in order for the X-rays to penetrate the part and to make it to the IR for signal processing. The kVp needs to be set at a level that will balance transmission and absorption of the beam through the part being imaged. The higher the kVp, the lower patient dose, because the less will be absorbed in the patient, just more will be transmitted through the patient. The opposite is true as well. The lower the kVp, the higher the patient dose. Okay. Higher kVp, Compton will become dominant. So this will decrease the SNR because Compton is noise. Okay, so the signal to noise ratio, the noise will be much greater the higher the kVp. In the next lesson, we'll discuss how to reduce this scatter and how to reduce it reaching the IR through beam collimation and through grids in the next video. The mask that is set will control the amount of X-rays that are produced in the exposure, and a sufficient mask must be set in order to have enough X-rays to make it to the IR for signal processing. Okay, so we need sufficient technique in order to make it to the patient, but an increase in the mass has a direct effect on the patient dose. Okay, so if we increase the mass, if we double the mass, we're doubling the patient dose. Okay, if we half the mass, we're halving the patient dose. So the goal is to get enough signal to the IR for image processing and balance the patient dose. So that's the goal. So the radiographer must be able to take in all the factors that go into producing a proper image, and they must think about all those when setting the technique at the console. Okay, so exposure indicators. Due to the robust pre and post process image processing that occurs during the acquisition of the radiograph and the wide latitude of digital receptors, a visually acceptable final image can be achieved with a less than acceptable technique. Okay, so our goal is to have a proper technique. Okay, due to digital processing and the wide latitude, exposure latitude that is afforded by the digital receptor and all these and everything else, it's possible to not be utilizing the best good techniques or proper techniques, and the image could still look acceptable. All right. Us as quality radiographers, that's our goal. Our goal is to use quality techniques. This can result in poor quality radiographs and overexposure of the patients. Okay, so overexposing a patient's not being a quality radiographer. Therefore, an X-ray system will communicate with the operator by an exposure indicator. So even though it looks visually appealing, right, the equipment's going to communicate to us back by some kind of exposure indicator, and it's usually a number value. Exposure indicators reflect the amount of X-ray exposure to the image receptor or the PSP with CR. Exposure indicators. So different manufacturers will have a various range of values that are considered a suitable IR or PSP exposure amount. These include the S number by manufacturers such as Fuji, Philips, and Konica, which is inversely related to the PSP exposure. This sounds like it's more for CR there. CareStream uses an EI that is directly related to the patient, to the plate, and changes logarithmically. AGFA uses LGM, which is log mean, and is directly related to the changes logarithmically. Also, there's things like dose area product, reached exposure value, and dose indicator. Okay, and all these might be used by different manufacturers. So it's our job to know what equipment we're using and what the proper readout values are, and that we're staying within that range. Okay, we're not overexposing the patient, and we're also not severely underexposing in passing low quality images. So some standardization has occurred with terms like EI, which is exposure indicator, EIT, which is exposure indicator target, and DI, which is deviation index, being set and adopted. So if an image is underexposed, it should not be repeated unless the radiologist defines the level of noise unacceptable, okay, that quantum model that we talked about, okay. A dark image should not be repeated no matter the level, unless something's called saturation has occurred, and saturation is the condition in which the detector elements like reach the maximum charge that they can hold, okay, and they're just blacked out. So we saw some of that in those images before, where we're doubling the mass, and some of the tissue was just completely blacked out. Okay, so those areas we would consider saturated, okay, and we'd probably want to repeat those, even though we used a very high technique, which the patient was now exposed to unnecessarily. Okay, so this is our role. This is our job with technique, okay? Further discussion of exposure indicators is delved into on the advanced topics of radiology playlist on this channel. Okay, so we talked about a lot of different concepts today that with technique and throughout this series, and this is a table that describes or that lays out what will happen with an increase in certain parameters, okay? And intensity, which is also the quantity of the beam, and energy, which can be the penetration or the quality of the beam, okay? And this is for the beam reaching the patient of the remitted beam, okay? Is these results right here. So, not necessarily the primary beam. So, an increase in KVP, the X-ray energy will increase, okay? The X-ray intensity, I said energy, the X-ray intensity will increase, right? And the energy will increase. With MA, exposure time or mass, because all these are, mass is just a combination of these two, right? And if we increase one, it increases this. If we increase this, it increases this, right? So it's directly related. So an increase in mass, exposure time, or the MA. The intensity, which is the amount, the quantity of the X-rays will increase, okay? And it will increase directly. The energy won't change. That's important to know. The distance, if we increase the distance, if we move the distance farther back, okay, the intensity will decrease. And we know how much it will decrease. It will decrease by by the inverse of the distance squared, okay? 1 over the distance squared, okay, is how much it's going to decrease, okay? The energy won't change, okay? The energy of the beam won't change, okay, because that's set by the KVP. Voltage ripple, which we'll talk about in the physics playlist, that has to do with the generator, okay? But an increase in voltage ripple just means that there's more up and down to the energy coming in, okay? There's more up and down to the energy coming in. So the average energy, okay, of this wave here, right, is going to be lessened. Can I do a pin? Yeah, I can do a pin. So the voltage ripple, a great voltage ripple, will be like this. So the average energy is going to be lower, right? Less of a voltage ripple, okay, where the energy is going to be higher, averaged higher, okay? So the intensity is going to decrease. Okay, so the amount of X-rays produced are going to decrease. Also, the energy is going to decrease, okay, with the voltage ripple. But we'll talk, there'll be a lesson on this that you can find in the physics playlist, all right? And this is why maybe room to room, the technique you use, or that it shoots at, is different, okay, because of the generator. And there's all the other factors that go into it, okay? Filtration, as we talked about, as we increase the filtration, the intensity will decrease, okay? So the amount, because we're filtering out some of the X-rays, will decrease, all right? The X-ray intensity or the X-ray energy will increase. Okay, so the average energy will get higher, but the filtration, okay, as it's increased, the amount will decrease. This is a chart that really summarizes everything we've talked about or that has been mentioned in these last lessons. Take all that and use it when you are X-raying a patient. This is another look at the chart here. I put it sideways because it may look better on your device. It's taking up more of the field of view this way. As you're going through your career and or your schooling, you should be watching when using the AEC in the rooms and at what kVp and mass the machine is shooting at. Then over time, you can get a range and like averages of the values to use for different views. And this is important because then you can set a fixed technique on your own. Remember, the AEC, which is discussed in the physics playlist, will not operate correctly if the patient part is not completely occupying the AEC area. So it will either shoot too light or too dark in these situations. A fixed technique will work regardless of this, whether the part's taking up the whole area. Also, on potables, the large majority don't have AECs. From my understanding, some do. And when setting your own technique, these factors need to be considered right here. Maybe all the factors, maybe just a few, and also patient factors, pathology, age, etc. Also consider that in the rooms, it's when you're using a bucky, it's utilizing a grid, which we will discuss in the next video. And each system may shoot slightly differently because of the generator, the age of the system, differences in the tube, and the manufacturer. Also, when you're work on becoming good at setting your own technique. So when you're in a situation when you need to set a fixed technique, you can do it correctly the first time. I often set my own techniques even in the room, and I know the exposure or at least exposure wise, I know that the image is going to come out good. The 15% rule answers. So let's go ahead, let's go through the answers. So an exposure is taken at 60 kVp and 32 mass. In order to maintain IR exposure, what should the new kVp be in order be when 16 mass is used? Okay, what should the new kVp be when 16 mass is used? So right off the bat here, we're going from 16 to 32, or we're going from 32 to 16, so we halved the mass. So with the 15% rule and we half the mass that we're utilizing, we're going to have to raise the kVp by 15%. That's my initial thought here. So, yep. So its mass is reduced by half, so kVp needs to increase by 15%. And so if we increase the kVp, which was 60, it said in the question, by 15%, which can be done like this, or it can be done 60 times 115 divided by 100, okay, because a percentage means of 100, we get to 69 kVp. So the new kVp we need at 16 mass is 69 at 16, or 60 at 32 will produce roughly the same IR exposure. And exposure is taken, the next question, at 76 kVp and 4 mass, an increase of 5% in the kVp is set for another exposure. What will the new kVp and mass be in order to maintain the IR exposure? Okay, so it's only given us two parameters here. Well, this one gave us three things, right? But we can figure out the other one. So we know right off the bat, increasing 5% in the kVp is set. So we can easily figure out the next kVp by multiplying this by 1.05 because we need to increase it by 5% is what it says. Okay, we can get the answer to what the new kVp is. When we do that, we talked about before, we need to reduce the mass by 30%. Okay, so we go ahead, we increase the kVp by that 5%, and we find out that it's 80. Okay, we can't use 79.8, but we can use 80 kVp. Now we need to reduce that mass by 30% in order to maintain the IR exposure. With this, the mass needs to be reduced. So 4 times 0.7, which is 30% decrease, or we can do it this way, we got 2.8 mass. So the new technique that will produce the same, maintain the same IR exposure is 70 at 2.8 mass. Okay, and with this, we've also reduced the dose to the patient, if we remember this. Okay, so this is a useful thing to reduce the dose to the patient. We can in practice. So let's look at the next question here. Exposure 1 is 54 kVp at 3.2 mass, and exposure 2 is 62 kVp at 1.6 mass. What will happen to the average energy of the beam from exposure 1 to exposure 2? And then it's also asking about the IR exposure. I hope, just right off the bat here, from exposure 1 to exposure 2, the average energy of the beam, you have the answer. Right there. Exposure 2 is going to have a higher average energy, because the only thing that we're changing that we know about here is the kVp is going up, so the average energy is going to be higher. Now IR exposure. The average energy of the beam will be increased in exposure 2, as we said, so we need to go ahead and compare the exposure to the IR. So we'll compare exposure 2 to exposure 1 with the kVp. So we put 62 over 54, and we see that the kVp has gone up 1.148, which is about 15%, okay, increase. So we know that that means that the exposure to the IR will be doubled with this 15% increase in mass in kVp. Now let's look at the mass. That means that the mass needs to be reduced by half. Let's say that. So on exposure 2, the mass needs to be half of what it is in exposure 1. We can look at it and kind of tell, but let's do it mathematically in order for both of them to be equivalent. So from exposure 1 to exposure 2, it's doubled. Okay, so exposure 1 is double the mass of exposure 2. So therefore, the IR exposure is the same in both techniques. All right, so let's look at the mass answers and questions that we asked earlier. What is the mass with 600 MA in 15 milliseconds? Okay, so right off the bat here, we're gonna need to take a pause here. I'm gonna need to look because we have the time in milliseconds, so we can't just multiply these two straight. Okay, this should like kind of ring something here when it's in this form. So we're going to go ahead and we can just divide this 15 by 1,000, right, to get the milliseconds into seconds. So if we divide by 1,000, we're dividing by 10, dividing by 100, dividing by 1,000, right? We're going to have 0.015 seconds times 600 milliseconds, and that's going to get us 2 millisecond amps, okay? So we'll go ahead, we'll do that right here, and we get 9 mass for the answer. The next question, what time is needed for 12.5 mass with 400 MA set? All right, we'll go ahead and we'll set up the equation. MA times time equals mass. We have the mass, we'll put it over here. We have the MA, we'll put it here. And that's what we did right, and that's what's done right here, okay? We'll make this semi-complicated, okay? And we'll, just to be more mathematical, we can easily divide this by 400 right here. We could divide that by 400 right there, okay? And we'll get the seconds out, the MA and the MA will cross out, we'll get the seconds out, and we'll get that. But we're going to do it a little more complicated, why not? So we'll divide this by 16. We'll put the mass on the other side by dividing by seconds. Okay, so now we have 1 over seconds over here, which is the same as 1 to the negative power of -1, seconds to the -1. With this right here, we get 25 for the answer. And now we need to flip it, okay, to get this to seconds. All right, so 1 over 25 equals seconds, and that just equals 0.04 seconds, which is also the same as 40 milliseconds. So if we do 40 milliseconds times 400 MA, we get 12.5 mass. Okay, this was a much more complicated way to do it, but you could certainly do it that way. But it's fun, and you can just take a bit of time if you struggle with this to see how all this worked out also, right? But the much easier way is to divide by 400 there and there. What is the mass with 100 MA in 0.2 seconds? Okay, so what's the mass with 100 MA in 0.2 seconds? Well, here we don't have any millisecond issue here, right? So we can just go ahead and multiply these two together. When we multiply these two together, we get 20 mass. Okay, so this is 200 milliseconds, and 100 mass, we get 20. 100 MA, we get 20 mass. All right, so let's finish up the questions and answers. What is the MA with an exposure of 120 mass in 500 milliseconds? So we can convert this milliseconds to 0.5 seconds, okay, and then we can set up the MA is unknown, MA times, we can write it out, we can set up MA, right, times 0.5, right, and equals the 120, okay? And then we can divide this out and we'll get the mass. That's one way to do it. We can also, just to show you a different way, we can also keep this here, right? We can convert this to milliseconds and we can just take the unit with us, okay? So milli is times 10 to the negative 3, all right? Milliamps, take the unit with us, take the milli with us with the amp seconds here, okay? And then we can just divide this by this. So if we divide this by this, these two cancel out right here. And then 120 divided by 500 will equal the MA, which equals 0.24, which equals 240 times 10 to the negative 3, which is milliseconds, okay? So that will equal 240 milliseconds, okay, if we're saying it, or 0.24 seconds, right? That's just a different way to do things again, okay? What time is needed to match the intensity of the exposure taken with 750 MA in 3 milliseconds when 250 MA is set? Okay, so we have one exposure at 750 MA in 3 milliseconds, and then we're saying when you're doing another exposure and we want to keep the intensity the same at 250 MA. All right, so let's look at that. So we need to convert the milliseconds is the first thing. So we convert that into seconds. We multiply that out. We get that the first exposure is taken at 2.25 mass. Okay, the first exposure is taken at 2.25 mass. We want to keep that intensity the same with 250 MA. Okay, so we know what the mass needs to be already. We got 250 MA, so we can just put the 250 MA here, right? The time is unknown, and then we can set it equal to the 2.25, okay? And that's what we'll do right here. We can divide both sides by the 250. These MAs, as far as units go, right? The MA over MA will cross out, and then we'll only have seconds left. So this works out very good because we want to know the time. We want to know the time. All right, so when we do this equation here, out we get 0.009 seconds or 9 milliseconds. All right, so if we think about this intuitively, since these numbers are relatively nice, we have 750 MA and we have 250 MA, which is a third of the MA. 250 plus 250 is 500 plus 250 is 350 or 750 MA, right? So we did this by a third, so we would naturally need to increase the time by 3. If we increase the time by 3, we get 9 milliseconds. Okay, this is very mathematical right here. okay, which will always get you the right thing, or once you understand the concept very well and intuitively, you can see this relationship right here between these two, and you're going to increase by a factor of 3 on the time in order to achieve the same mass. All right, so this concludes this video on technique. I hope the information here was useful and these examples were useful. We also talked about exposure factors and quantum mottle, and we talked about distance, how it affects. In the next video, we'll talk about grids and beam restriction, okay, and collimation.